2 go all right for everybody? Everything tomorrow Saturday, so that I can sleep in. Hope you guys all have a restful weekend also. Couple of quick reminders. We did have lab this week, and the assignment, whether or not you hand in a physical copy or just email me a digital copy, anything is fine as long as I have it by the end of the day today. Some people have been emailing me in either scanned images of what they've been working on, or literal pictures of what they've been working on, or just the document with their answers typed in. I've also got a pile of paper ones right here, including a few that are just answers on a separate sheet of paper. That is also fine, as long as I have your answers and your work in some format by the end of today. Additional reminder, our first homework assignment and our first quiz are currently on the Sapling website. They're currently both set to be due next Tuesday. That way, we'll be able to go over everything today in class, and you'll have the weekend to work on it. And then on Tuesday, you'll be able to come in with any questions that you have and ask them before it's due later that night. That's how I plan on it being in general. If I need to adjust it a little bit, depending on how long it takes us to get through a couple more examples, then I will. Again, I will only ever make an assignment due later than I originally made it. I will never make an assignment due earlier. So, lab due today, homework and quiz currently due next Tuesday. We're going to be wrapping up Chapter 1 today and the start of next week, and we'll be beginning to move into Chapter 2, which is about forces. So, before we continue, get onto all of that, does anyone have any questions? All right. Well, let's go ahead and get started. It's Friday. The sooner we begin, the sooner we can end, and the sooner we can at least begin getting towards our weekends. I hope you all have wonderful ones. So, we ended last time with a discussion of gravity and why objects fall. So, what do we consider to be the constant g, or acceleration due to gravity on Earth's surface? Very good. Negative 9.8 meters per second squared. Negative means down. Meters per second squared tells you that this is an acceleration. And does an object's weight affect this number? No. Every object that we are going to be looking at is going to fall at this rate as long as the problem takes place on Earth's surface. So, again, keep that number on hand. That this is going to be the rate that all objects fall at, and we're going to be more closely examining objects in a specific state today. Falling is kind of a vague term in the English vernacular. In physics, we have better defined the state of free fall. And an object that is in free fall is an object where when gravity is the only force affecting the object. So, if an object is strapped to a parachute and is then thrown off of the building, is that object in free fall? If an object has a parachute, like if you have a parachute and then you jump, is that object in free fall if it has a parachute? No. Very good. The whole point of a parachute is to increase air resistance so that you don't accelerate at this particular speed. So, in the case where air resistance is very high, the object is not in free fall. specifically, we see this for parachutes, we see this if you drop just a single piece of paper. Those are specific exceptions to the rule where air resistance is so high that it actually does affect the rate at which something will fall. So if something has a parachute, it is not in free fall. What about a plane? Okay, so if the plane's engines are turned off and it is falling out of the sky, sure, but very, very good observation. But what if the plane is in flight? What if it is actively flying? It wouldn't be in free fall if it is currently flying, because if something is in flight, there is a force opposing gravity to hold it in the air. So, objects with parachutes are not in free fall. Objects that are flying are not in free fall. Same thing with, say, a missile. It has a propulsion system. It is being blasted by a rocket, and there is some force keeping it in the air. It is not simply falling down under only the effect of gravity. If you climb a rock wall and you have that harness on that slows your descent, is that free fall? No. So, there's a lot of things that aren't free fall. Free fall is just when the only thing acting on you is gravity. But that can itself create a unique scenario because you can be in free fall while going up. If I throw this marker straight upwards, the second it leaves my hand, the only force acting on it is gravity. Even though it's still moving upwards originally, and I can't catch, even though it's moving upwards originally, gravity is the only force affecting it the second it leaves my hand. Therefore, even as it rises, it's in a state of free fall. It is technically falling as it goes up. So, free fall does not always mean going down. Granted, it does eventually come down. It has to, because it's accelerating at this rate down. But at least originally, it can be doing this. It can be accelerating downwards as it rises. So that's an important distinction to make, because we're about to work an example involving an object rising even though it is accelerating downwards. Any questions before we begin with that example? Okay, so we're going to be examining the jump trajectory of a fictional basketball player. This person is able to jump off of the ground as a standing high jump where they leave the ground at 6 meters per second, which is actually very fast. So, always helps to read the questions, list what you do and don't know, and draw pictures. Let's read the whole thing first. The basketball player leaves the ground with a speed of 6 meters per second when he jumps vertically upwards. First question is, how much time did this person spend in the air? So, I'm going to draw a picture first. You've got our athlete here. This person is going to jump vertically upwards at 6 meters per second. And knowing what you guys know about physics, you've been jumping and watching things be thrown directly upwards your whole lives, what's going to happen to this person after they leave the ground? Okay, they're going to rise and they're going to come back down. As they say, if all things that go up must come down. They also say, I can't catch. So, we know, before we list any more of our variables, we know this person is jumping up at this initial speed, they're going to rise, and then they're going to come right back down to the ground. We can pull some numbers out of this that will help us later. Just from this picture, just from that understanding of how jumping works, we're going to be able to pull some more variables here. But first, let's go ahead and list our 6 meters per second. Now, examining this picture, this person is going to begin on the floor. What can we say about that as our starting location? If we're trying to list, say, displacement, what is our starting location going to be if we're on the ground?
0.
Right, we can just go ahead and declare that our starting location, our starting distance, is 0 meters. We're beginning on the floor. And as soon as this athlete leaves the floor, as soon as the floor is no longer touching them, gravity is the only force affecting them. So what's one more piece of information we can go ahead and add? Very good. They're going to accelerate at the rate of gravity, negative 9.8 meters per second squared. The problem did not specifically give you that number, but you know after they jump, they'll be falling in a state of free fall, and you can assume that number as well. So, this is some of the information that we have been able to pull from the question. And the first thing we are asked for is what is the total amount of time this person will be in the air. So the amount of time from here to here. So, read the question, draw a picture, listed what we know and what we want. Next thing we should do is consult our formulas. So I'm just going to back up to the page with formulas on it. These are the formulas we've talked about so far. With what we know and considering what we know and what we want, being time, what formula do you think is going to best help us here? One more time. Okay, so the bottom one contains final velocity squared. We haven't listed that yet. I'll teach you guys an assumption we can make about that in a minute, but let's just keep looking at this particular formula first. We do know initial velocity. We know acceleration. We can make an assumption about displacement, but this particular formula cannot help us solve for time.
Oh, maybe it's acceleration.
It is an acceleration question. Yes, there is an acceleration. So if we want something that has an A and a T in it, this is a useful formula. This one will actually be useful in a minute. So we're going to save this one for later. This one will help us in a second. But we need one that has both an A and a T in it to be able to find time in the air. So that only leaves us with these two, number 2 and number 3. Which one's going to help us the most right now? This one? Well, really we could use either one. But I'm going to help you realize another assumption here that will make the formula choice a little easier. Notice we begin here on the ground and we end here on the ground. So over this total amount of time, what is your total displacement going to be? Zero. You begin, you end where you began. You did move during the jump, but at the time we're looking for, you've gotten back to where you started, therefore your total displacement over this amount of time is 0. So I'm going to list distance final as 0 meters, go right back on the ground. So we know our initial location, our final location, and our delta, our change in location as well, our total change in displacement over the whole thing is just going to be 0. So we know delta D, which again, I'm sorry, that formula listed as delta X. So we know delta D, we know change in displacement, we know initial velocity, we know acceleration, we want time. With all of that information, without having to make any further assumptions, formula 3 seems like our best bet at the moment. without having to make any further assumptions or pull any more data, we use formula 3 to help us solve for time. Cool so far? Okay. Now, and 3 is a very good one to, honestly, 3 is going to be your best bet a lot of the time. It's a better version of Formula 1 because it allows you to track an object as it moves, as it accelerates, and this person is going to be accelerating the entire time as they displace. So, let's go ahead and write in our formula. Delta x equals the initial times time plus 1/2 a squared. So, our change in location, our change in displacement over the whole process is just going to be 0. It's going to end where we began. Our initial velocity is 6 upwards. We are solving for time, so that is going to, we're going to leave that as t for now. Plus 1/2 times our acceleration, it's going to be negative 9.8 because we're in a state of free fall. And then times time squared. So that leaves time as our only remaining variable. We can solve for time using this. As you guys copy everything down and get to this point, does this look kind of, does this type of equations, the way this is laid out, look kind of familiar? Say again? Okay, very good. It's okay. If you, it's not a thing that ever comes up outside of an algebra class, but the fact it looks familiar is very good. I'm going to rewrite this slightly to help show what it is. All I'm doing is just the next step in the algebra. We have, exactly. This is, or can be made into, a quadratic. What that tells us is there's really 2 times where this athlete is on the floor. One is at the beginning, where t equals 0. The other is x seconds later after they've landed again. So there's 2 points in this trajectory where you are on the floor, which really we only care about the time afterwards, but technically, yes, since you begin on the floor, t equals 0 is one mathematical answer. Because this is a quadratic, we can do the quadratic equation to get those answers. And that equation has been coming up for a question in the lab. I've been putting it on the board for everyone to copy down. I will, don't really have this. Okay, I'll erase free fall to put it up on the board for those who haven't copied it down yet. It is something that it will help you to know. You don't necessarily need to memorize it, but you do need to recognize it. We can use that quadratic equation to get our answers here. But there's actually a shortcut we can employ because we kind of lucked out how our variables came through here. Our C term is a 0. That means we can actually factor out one of these t's using the distributive property. So you don't have to change anything in your notes. I'm just going to show you this. We can divide a t out from both of these. That's just going to leave us with negative 4.9t plus 6 times t. This whole thing is now equal to 0 if we divide both sides by t, 0 over t is 0, this t just vanishes. This is the t that if you work the quadratic would tell us one of the times you are on the floor is at 0 seconds before you ever jumped. It's not the one we're looking for, so we can just go ahead and take it out. And doing that simplifies it to where we don't have to bother with quadratic today. Does that make sense? Okay. Quadratics will come up, and being able to notice when you can do this trick will save you some time. So if c equals 0, if the c term in your quadratic is 0, you can skip this one step and it'll make things a little bit faster. That leaves us with, or will leave us with, negative 4.9t plus 6 equals 0. Subtract 6 to the other side. Oops. That's going to give us negative 4.9t equals negative 6. Therefore, t will be equal to 6 over 4.9, which is about 1.22 seconds. Which, again, that might not seem like a long amount of time, but that is a decent amount of time to be in the air in a state of free fall. Yes?
So, okay, so when we divided t out to reduce like the t squared, in order to get from 1.92 plus 6, 0 to multiply t on that side to the 0, and that's where it went?
Yes. We distributed this t out. If we divide both sides by t, that cancels this t out. That would make this side at 0 over t, which is just 0. So we threw it into a black hole and got rid of it. Dividing by 0 is 0, but 0 divided by anything is also still 0. And that tells us time in the air. That's the total amount of time from start to finish. Questions about getting to this point? Okay. So, we found the answer to the first part of the question. That's how much time was spent in the air after this high jump. The next question is, how high was the jump? If you were in the air that long, if you were able to jump up at this speed, what is the height you will reach? I'm going to fill in the time we just solved for. So we know over this amount of time, we're going to go from the floor back to the floor. We've been looking at this as a case of from start to finish, from floor to floor. But now we're examining the middle state. We're looking at this spot now. And that's technically a different point in the question. It's a different displacement. This is a different height. It's going to be a different amount of time in, and we're going to be at a different displacement from the ground. So instead of looking at D final, we're now going to start looking at D middle. We want to know our displacement at a specific point in time, not just at the end. Now, to get this particular answer, you have to be able to make one of two different assumptions. I'm going to teach you both of them. The first assumption you can make here is, it takes 1.22 seconds to jump up and then come back down. You're going to jump up to some height and then descend back down to the same level. Two halves of this journey are symmetrical. You begin rising at this particular speed, you come up, and then you cover the same amount of distance at the same acceleration going back down. Realistically, it should only take you half of this time to reach your max height. You spend half that time rising and then half that time descending. So we can assume at what time you would be up here. As long as you start and end at the same height, it takes as much time to rise as it takes to fall. So we could make an assumption about, time in the middle, like the time at the point we're looking for being half of 1.22. That is one approach we can make. That is an assumption that you can make in questions like this. But there's another assumption we can make that is that I want to stress as sort of a more universal truth that a lot of people don't immediately realize. I'm going to throw this marker, and I want you to pay attention to what happens to it as it hits that top point. If I could throw properly. Okay. So for that split second at this peak, it's just suspended there. It's hanging. What is its velocity at that point? 0. We can assume that the velocity at this particular point is 0. So when any object is thrown or launched or fired upwards, it has an initially upwards velocity, but even then, the entire time, it's accelerating down. You can move up and accelerate downwards. That is what happens as you fall. You begin at some positive speed, and even as you move up, your speed, your velocity, starts dropping from 6 to 0. It's becoming more negative the entire time. It's decreasing. So for a split moment, if you could freeze time right here, velocity is 0. You're not moving. You're just hanging there. And then every second after that, you go from 0 into the negatives. You accelerate from 0 back down. Another assumption you can make, actually, can you guess what speed, what velocity you'll be moving at the very bottom before you hit the floor? Say again? My ears aren't great. That's the acceleration, yes. So you'll be accelerating at that rate. But what will your velocity be? The actual, what the speedometer would say right before you hit the floor. Well, at the top you're at 0. The thing is, if you start and stop at the same height, the velocity, this velocity will be the same, but downwards as your launch velocity. Over this distance, you accelerated from 6 to 0. And you're going to fall at the same, you're accelerating at the same rate the entire time. Your velocity is changing at the same rate constantly. Which means if you go from 6 to 0 over this displacement in a specific amount of time, and then you fall that same distance and it takes the same amount of time, you're going to accelerate to the same speed, but in the opposite direction. This athlete is going to land at -6 meters per second. The two halves of the journey are completely symmetrical, just pointing opposite directions. Cool. Again, this is something that you probably understood even if you've never consciously thought about it. The harder you throw something, the higher it will rise, and then the faster the harder it is then going to hit your hand. It's going to come back down and be at the same speed as long as it falls to the same height and you catch it. You have to start and stop at the same height for this to be true. But if you do, it'll take half your time going up and half your time coming back down, and you'll end at a negative version of your original launch velocity. All of these assumptions combined, we can use to help us find this height. We know at that top point, we're going to be moving at 0 meters per second. We know we originally launched at 6 meters per second upwards. We want to know how much higher we are at that point, and we know our acceleration. This, to me, indicates a good time to use equation 4. We know at that point our velocity at that particular time. We can use that 0 for VF. We know our initial, we know acceleration. We want to find displacement up to that spot. So, in any problem, your final velocity, any variable with a final on it, is final to the point of time that you're looking at. We do know that, from beginning of the jump to end of the jump, this is where we will end up. But if we're examining this spot right here, then we can plug in all of our variables from this spot as our final. Initial is just where are you beginning, and final is where the point to which you are examining. So even though we know a different part of the question ends here, we can use variables from here and plug them in for our final variables in the equation, because this is the point in time we care about right now. So, since this is the point in time we care about, this is our velocity at that point in time. Plug that in for VF, 0 squared equals our initial velocity, 6 squared, plus 2 times our acceleration, times our displacement. And this will be our displacement from our initial to the spot we're looking at, which is the change in height. That'll tell us how high we are. Questions so far? I'm talking a lot. Okay. So we've got everything plugged in except D. Let's solve for D. Just going to simplify the next line. What's 6 squared going to be? Very good. And what's 2 times negative 9.8? Very good. That's going to be times D. Realize my 6's and D's look very similar but backwards. So D is still the only thing we have left to find. We can just rearrange and solve from there. This term is negative, so in my head it makes the most sense to add this to both sides. That way it gets rid of the negative sign. So I would write that as 19.6 D equals 36. Last thing you need to do is just divide both sides by 19.6, and that will tell you your final answer. Did someone just say the number? 1.8. Very good. That's going to be 1.84 meters. That's nearly 2 meters, and each meter is about 3.3 feet. So this particular person, if you can jump at this speed, if this is your straight vertical jump velocity, you could jump to about that meter stick high. That's about 2 meters right there. So this is actually a pretty crazy jump speed, and that's a pretty crazy jump height. Sorry? Sorry, I thought someone said something. My hearing's not good on a normal basis, and I think masks, everyone's masks are just making it harder for me hearing, which is not your fault. I just might need to ask you to repeat yourself every so often. Okay, so any questions about this particular case? Particular example. Okay, I wanted to get through the example, so I just kept, I realized we've been talking about working for a minute. Does anyone need water? No? Okay. Hope week 2 has gone well for you guys. Really, as the weeks go on, my workload just keeps increasing because now I keep recalibrating more and more labs as they keep coming up. I'm, again, trying to figure out the best way for everyone to be able to use the marble cannon in the lab next week, actually, so that we can actually launch something and examine its trajectory and figure out where it's going to land. So I'm hoping I can get that working in one for everybody. So who doesn't like to they're spring-loaded, though. They're just spring-loaded cannons. So it's just kind of a tradition of the department. Every class begins with a cannon. Okay. Any questions? I'm just gonna introduce the next topic. Introduce it before we break. I'm not going to give you any math before we head out. But I want to at least talk about the distinction between an object that is just falling straight down versus an object that has been thrown. So, I have 2 separate markers right now. I'm going to drop the red one straight downwards. Meanwhile, I'm going to try to flick the black marker horizontally. So this marker is going to be projected horizontally. This one is only going to be dropped straight down. Which one should hit the floor first? Okay, now why do you think that? Say again? Okay, you just have a feeling. Honestly, like I said, you've been watching physics your whole life. Sometimes you don't even do the math, you just have a feeling about it. So, red marker is just going to drop straight down. Black marker, I'm only going to throw it sideways. I'm not going to throw it up, I'm not going to throw it down, I'm going to launch it sideways. Okay? At least I'm going to try to. Everyone ready? It sounded like they hit at the same time. Now, most good experiments, you want to do it multiple times. You want to get multiple data sets. So I'm going to do it again, at least one more time. So I know not everyone can see where they land, so just try to listen for the thumps. Those in the front, if you could corroborate that they hit the ground at the same time, when you can see them, that would be helpful. So. They're hitting at the same time. That is because this is now 2-dimensional motion. The red marker I'm only dropping straight down, so it's still moving 1-dimensional. The black marker, I'm throwing it sideways. I'm throwing it in this axis, the horizontal axis, which is separate from the vertical axis. The reason that they're both going to still hit the ground at the same time is Earth's gravity doesn't care how fast you move sideways. Earth's gravity is still going to pull everything down at this rate. Both of them have an initial vertical launch velocity of 0. Both of them are starting at the same vertical velocity. I'm not throwing either of them straight down. I'm not throwing either of them straight up. They're both falling from the same height and from the same vertical launch velocity. Earth doesn't care how fast you move sideways. It's only going to pull you down based on vertical components. That's because the x-axis and the y-axis are separate axes. What happens in one axis has no effect on what happens in another axis. You can be moving sideways all you want, you're still going to fall at the same rate. Now, granted, if I threw the black marker upwards, would it hit the ground at the same time? No. I'll show that now. That's because in that particular case, the launch velocities are different within the vertical axis. But if I throw it sideways, it will stay in the air the same amount of time, it'll fall at the same rate, they'll hit at the same time. So your mass does not affect your acceleration down, and whether or not you are moving horizontally does not affect your acceleration down. As long as the two objects have the same vertical launch velocity and are dropped from the same height, they'll hit the ground at the same time. So, key takeaways here. I could add a couple more things for you to write down here. So, the x and y axes are completely separate. What happens in the horizontal axis does not have any immediate effect on the vertical axis. So, regardless of whether or not something is dropped or thrown sideways, they'll still hit the ground at the same time. The x and y axes are separate. Sideways movement does not affect vertical falling. This is your introduction to two-dimensional motion. When I throw a marker sideways, it is moving in two axes at once. It is falling down through the y-axis, and it is moving sideways through the x-axis at the same time. It is moving in two axes, two dimensions at once. Next week, we're going to begin working some sample questions about this. The sort of applications that this have is we're going to be able to use this to calculate the range of a projectile to figure out where something is going to land. And that's what we're going to be doing with the Marvel camera. We're going to be able to predict where your target, where to place your target so that you hit it with the camera. Cool? So, everything we've talked about so far, work on your homework, finish your lab, make sure it's due by the end of the day. Do be working on your homework over the weekend. Quiz is the last thing you do, so make sure you're done with the homework before you start the quiz. But take as much time, as many tries as you need on the homework. Email me your questions as you have them, please. The only reason I will not answer your question or help you is because I'm asleep or driving. All right? So, be working on those, and you have a wonderful weekend. Thank you all.